Welcome back everyone to this lecture series on convolutional neural networks on custom images. So this is part 1, and in this custom images CNN lecture series, we've already gone over how to load in custom images and perform transformations on those images. Now what we're going to focus on is how to actually train on those custom images, how to load them and feed them into a convolutional neural network. And we'll be using a very similar convolutional neural network to what we applied to for the Safari 10 dataset. And then we'll learn how to evaluate this model. And then after all this, we'll learn how to use pre-trained models. Since training on custom images typically takes a really long time, you can save a lot of time by using pre-trained models. So again, we're going to be working with this image set of cats and dogs. So we can see here that these dogs and cat images vary widely, and we can also see that we're going to be performing transformations on them. So you can see that some of these have been rotated. And the convolutional neural network architecture we're going to use, very similar to what we did on the Safari 10, we'll have 2 convolutional layers feeding into pooling layers. We'll start off with 6 filters and then go to 16 filters, and then we'll eventually reduce that using fully connected layers. So after that series of convolutional and pooling layers, we end up having 46,656 parameters that then we fully connect and start flattening out and reducing to 120 to 84, and then finally to just 2 output neurons, since we're only dealing with 2 classes. Previously we used 10 output neurons since we had 10 output channels or 10 classes, but in this case we only have either cat or dog, so we have 2 final neurons. So at the end of that, we'll get something that looks like this. Okay, let's go ahead and get started and head over to the Jupyter Notebook. All right, here we are at the Jupyter Notebook. I've gone ahead and just copied and pasted the standard imports that we've been using. So this is just copied and pasted from the CNN on Custom Images notebook. And notice here for Torch Vision, one thing we added was this models. So everything else is pretty much the same, except we've added here models. So next what we're going to do is we're going to define the transforms. So in the previous couple of lectures, we looked at a variety of transforms available for data augmentation, such as rotation, flipping, etc. So now what I want to do is actually define that. So I will say train underscore transform, and then set this equal to transforms dot compose, and in compose we pass in a list of transformations. So what I've gone ahead and done is using a couple of threads on the PyTorch discussion board, and they're linked to you or for you in the lecture notebook. So if you go to the lecture notebook and click on the recommended normalization parameters, it'll take you to this discussion where we read up on some of the recommended normalization values. So that's where I'm getting some of these values from. I'll go ahead and close this out, and let's start with the transformations. So first what we will do is we'll perform a random rotation. We will say transforms dot random rotation, and this will be a pretty mild rotation. We'll just say 10 degrees, and these are values you can always play around with. And then we'll say transforms, and we'll also do a horizontal flip. So say random horizontal flip, and if you take a look at Shift Tab here, the default probability is 50%, so we'll keep that default probability. Next, what we're going to do is after the random rotation, random horizontal flip, we need to resize everything to make sure they're the same size. Based off what we saw for the mean and median sizes of the images, what we'll go ahead and do is say transforms dot resize to 224 pixels, and then transforms dot center crop, just as we did in the previous lecture series, again 224. So basically resize everything to 224 and then crop it so that it's basically as centered as possible. Then after all of that, we need to transform that into a tensor. So say transforms dot to tensor. And then finally after that, we'll say transforms to normalize this. And we'll use the same normalized values that we used last time from that discussion. And I'm just going to copy and paste them here from the notebook. That way I don't accidentally make a typo. And then we have our train transform object. Now we're going to create a very similar transform object, except this is going to be for the test set. So for the test set, what I don't want to do is randomly rotate and randomly flip these images, since we're really just using them to test out the capability of the network to predict on a new real image of a dog or a cat. And the real images in the dataset, those aren't randomly rotated or randomly horizontally flipped. So all I need to do here is make sure I resize and normalize them to the same dimensions that the test set, or excuse me, that the network has learned on. So you'll say test transform, transforms.compose. And what we will do is we're simply going to essentially copy everything after random rotation and random horizontal flip. So I'm going to grab these guys and then paste them in here. And again, because this is the test set and we're just evaluating the performance of the model using the test set, we don't need to do these random rotations or random horizontal flip. We just need to resize to make sure it's in the correct dimensions that the network was trained on, and also we need to normalize so that it's the same value range that the network was trained on. Okay, so we have our train transforms and our test transforms. Let's go ahead and load in our train and test sets using these data loader objects. And what we're going to do is we're going to take advantage of a built-in Torch Vision dataset called image folder. So if we come up here, there is an image folder off this datasets object from Torch Vision that we can use. So we'll go down and show you how to use this. First, we need to find the route path to kind of this top level folder. And in my case, it's under data, underneath cats dogs. And because of the way I loaded it up, I have double cats dogs. You probably will only have a single one, but just the way I unzipped it created double. So after this, if I hit tab, I should be able to see, besides these kind of default Jupyter, I should be able to see train and test. So if you see that, then you know you're in the right location. So we'll just say cat dogs as our root here. And then what we will do is go ahead and say train underscore data is equal to datasets. We're going to call image folder off datasets. And we say os.path.join. And we're going to join that root path together with train. And if you wanted to, you could just pass in manually the whole file path to your training data if that's easier for you. os.path.join, all it's doing is essentially concatenating this string with this string to tell you where the image folder is for the training data. So if you do shift tab here, basically it just needs where is the actual location of this training data for the root. And then after that, we need to provide a transform. So we'll say transform equal to train underscore transform. And then we'll have test data equal to datasets.image folder. And then same as before, we'll say os.path.join. And we'll join that root together, but this time with test. And the transform is going to be that test transform we made. So we'll say test underscore transform. And then that's our test data. Let's go ahead and beyond that, what we're going to do is now that we have these dataset objects, we'll make sure to shuffle them in the same way that mine are shuffled. And we'll set a seed. Again, 42, just an arbitrary number choice. Then we'll say train loader is equal to data loader. Pass in our training data. We'll set a batch size. And this is something you can experiment with. I found that a batch size of 10 performed pretty well. And then we'll say shuffle is equal to true. And then for the test loader, we'll say data loader test data. Whoops, make sure I spell that right. And we'll also have same batch size equal to 10. For the class names, what I'm going to do is say class names is equal to train underscore data. And because of the way the files are formatted, I simply need to say train data.classes. And keep in mind, you're going to need to organize your data in the same way that we've organized this into subfolders or subdirectories of train, and then the actual class titles as the name of the folders. So finally, let's go ahead and run this and make sure you don't get any errors. If you are getting an error there, please triple check your actual root here, or just manually provide it into this image folder. And next what we're going to do is just check out what those class names are. So those class names, notice that they're capitalized, cat and dog. It's because if you look at the subdirectories, cat and dog are capitalized underneath train and test. And next what we're going to do is check out the length here. So the length of the training data is around 18,000 images, and then the length of the test data is around 6,251. But keep in mind, we have this list of transformations we can perform on this. So essentially, as we're feeding in these randomly transformed batches, we're not just showing the same 18 or almost 19,000 images every time. We're showing kind of randomized rotations or flippings of them. So next what we're going to do is just display a batch of images. So to verify that the training loader selects cat and dog images at random, so we want it to be trained on cats and dogs kind of simultaneously, so it can not learn all dogs first and then learn all cats first. Otherwise, that won't lead to a generalized model. Instead, it'll perform poorly. So we need to make sure that it's feeding in both cats and dogs kind of randomly at the same time, and that we are performing those random transformations, such as flipping horizontally or the rotation. You won't really be able to tell if something's been flipped horizontally, since we don't know all the images, like what all the 19,000 original images look like, but we will be able to tell if something's been randomly rotated with the little black edges around. So first, let's go ahead and grab a batch of the first 10 images from the training data. We'll do this by saying for images, comma labels, in train, and this time we called it train loader. We'll go ahead and just run a break. So now images here, take a look at it. It's these tensor objects, and if I check the shape of this, notice it's 10 by 3 by 224 by 224. So there's 10 images, 3 color channels, where each channel is 224 by 224 because of these transformations we did here on resizing. Next, what we're going to do is we'll go ahead and show one of these. So I'm going to say IM is equal to make grid, images. I'm going to define n row as 5 since there's 10 images. We'll go ahead and do 5 images per row. And then keep in mind that we did normalize the images. So I'm going to inverse the normalization. I'm going to copy and paste this. We've already seen this inverse normalization before. So we've already seen these 2 lines of code from the previous lectures, essentially inversing that normalization. That way they actually kind of appear normal when we plot them out. And then we'll say PLT figure, just so I can expand on this figure size. I'll go ahead and make it something like 12 by 4. You can play around with that. And then we'll say PLT imshow. And I'm going to copy and paste the same line of code that we've already seen on the fact that we have to essentially transpose the axes in order to get the color channel to the correct dimension that Matplotlib expects. So we've already explained this before in the previous lectures, and essentially we've already seen all this code before. So when you run that, you should get something that looks like this. And if you used the same manual seed that I did, then your first batch should actually be exactly the same. You should see these actually precise animals. So you should see a German Shepherd here, a cat on the next one. Now what will be different is the rotation or horizontal flip. So you should see the exact same animals, but you should not see the same random rotations or random flippings. Okay, so next we want to do is define our model. Let's go ahead and do that. It's going to look really familiar since it's going to look really similar to what we did for the Safar dataset. So I'll just say class convolutional network here. We inherit from NN module. We say DEF init, pass in self here. We're going to call super dot underscore underscore init, and then we'll say self convolutional 1 is equal to NN conv2d, and remember, whoops, this should actually be equal sign, not minus, excuse me. And remember what the parameters here are. We pass in the input channels, the output channels, the kernel size, and stride. Then optionally you can continue on to padding if you wanted to, but in this case we won't do any padding. We'll just say that we have, whoops, 3 input channels. So we have those 3 color channels. We'll say create 6 filters out of them. Kernel size is 3 by 3, and go with a stride of 1. Next convolutional layer will be convolutional 2D. We'll say 6 by 16. So we have those 6 filters, or the result of those 6 filters being inputted. Then we're going to expand that. We'll say 16 filters, and then again we'll say 3 and 1. So a 3 by 3 kernel with a stride of 1. As always, you can experiment with these values. It doesn't have to be 6 filters, doesn't have to be 16 filters. Keep in mind, if you make the number of filters larger, your training time will take more. And then we'll say, start reducing this with the fully connected layers. So we'll say NN linear. And if we start doing the math here, we realize that the number of parameters being put in is 54 times 54 times 16. And how do we actually get that number? If we start doing it, we'll say, remember we have a 200 by 24 image, and then we'll say minus 2 because of the lack of padding. So as we actually perform that convolution, we lose the pixels at the very border on both sides. So that's -2. And then that's going to be divided by 2, since we're going to apply a pooling layer to that. The next convolution that we perform will again lose 2 on the borders. And then after that, we're going to pass it through another pooling layer, so that'll be divided by 2, which gets us 54.5, which in this case gets rounded down. So it rounds down to 54 pixels per side. So we have a 54 by 54, essentially reduced image, times the 16 filters. So that's how we get 54 by 54 by 16. And we actually have to decide how many neurons we're going to feed into that for next. We'll go ahead and do to 120. And you can choose more neurons if you want. Next fully connected layer, we'll start reducing this more and more until we get to those final 2 outputs. So we'll go from 120 to 84, and then we'll say self.fc3 is equal to nn.linear. Make sure I spell linear right. Linear. There we go. And then we'll go from 84 down to 2. And this may be too extreme to go all the way from 84 to 2, but you'll see we'll get pretty good results. You can always expand on this. And then we'll say forward self x. And now we're essentially going to provide all the forward methods here. So we're going to go straight into this convolutional network. So let's go ahead and do that. We say pass in from convolution 1, pass in our x data. That's capitalized here. And then we need to run this through an activation function. So we'll do rectified linear unit, since we know that performs quite well. And then we'll save the result of that. Next step after that is to go through a pooling layer. So we say x is equal to f dot max underscore pool. So we pass this into a pooling layer. So max pool 2D, pass in that result, and it's a 2x2 with a stride of 2. Which is a really common choice when we're dealing with these kind of simpler convolutional neural networks. Although you can always read up on research and different publications to see what pooling layers or what convolutional sizes or dimensions they use. You know, there's kind of no right or wrong answer if you haven't dealt with your data set before. You can always just look up on various publications what actual values they're using for stride or pooling, etc. Next, we go into the next convolutional layer. So we'll say f dot rectified linear unit, except this time it's going through convolutional layer 2. Then after that, we're going to do max pooling again. So we'll say max pool 2D. Go ahead and do 2x2 kernel with a stride of 2. And then we start going into the linear units. And we need to flatten this out. So we'll say x is equal to, and we're going to flatten out this data. So -1, because we want to be flexible to any batch size, so keep the same batch size. In our case, that will end up being 10. But we'll say -1, and then the number of dimensions is going to be 54 times 54 times 16, as we just discussed. And then we'll say x is equal to rectified linear unit being passed into those fully connected layers. So we first have fc1, then let me scroll down just a little bit here. Then we have f rectified linear unit self.fc2, passing that x, and then after that we have essentially our final one, which is f self.fc3 x, and we've passed that through the final activation function, which is not a rectified linear unit, but instead is the logarithmic softmax, because we're performing a technically multi-class classification with just 2 classes, and we need to do this along dimensions equal to 1. So technically, this isn't really anything new. We've seen all of this before, both on MNIST and CIFAR 10. You can always play around with the different values here as far as number of filters and kernel size and stride size. So kind of these last 3 are always up for grabs that you can edit and play around with, as well as the number of neurons you decide on the linear layer. The ones that you essentially have to hard code in are the fact that there's 3 color channels, that this next convolutional layer should be directly connected to this one, and then you have to perform this calculation dependent on your pooling layer, as we just performed it here. All right, and we're going to go ahead and run this, make sure we didn't commit any typos. Looks like that ran correctly. Let's go ahead and set up our loss and optimization functions, and then in the next lecture, we'll set up our training. So I will say torch.manual seed. Again, I'm just choosing an arbitrary value here, 101. We'll create an object called CNN model, create an instance of our convolutional neural network, choose our loss criterion. In this case, we choose cross entropy loss because we're doing classification. And then the optimizer we're going to choose, as usual, the Atom optimizer, since it performs the best here. CNN model, pass in the parameters, and we'll choose a learning rate of 0.001. 0.001, usually a good starting point if you perform really poorly with this learning rate, and maybe it's an issue with your data, but if it's not an issue with your data, maybe slow down the learning rate to 0.0001. But keep in mind, that makes training take a lot longer. So we run that. Always a good idea to check out our model, make sure everything makes sense. We have our convolutional layers leading into the fully connected layers, and let's go ahead and see how many parameters we have here. So we will say for p in model.parameters, print p dot number of elements. And whoops, this should be CNN model. There we go, let's run that. And here we can see that at a certain point we have kind of a huge number of parameters. And that's because of this kind of in features right here. So we're doing 16 filters, but remember, these images are much, much larger than what we've dealt with in the past. Previously, we've dealt with either 28 by 28 images or 32 by 32 images. And now we're dealing with 224 by 224 images. So these images are essentially almost 10 times larger than what we've dealt with before. So it makes sense now that at essentially the flattening out phase, we're going to have these really large number of parameters here. And keep in mind, this is already with the advantages of using a convolutional neural network. For this sort of image data that's 224 by 224, there's just no way we'd be able to train an artificial neural network on this because the parameters would just be in the tens of millions here. Since notice here, we're already breaching 5 million with a convolutional neural network, you can imagine just how inefficient an artificial neural network would be. So at this point, when we're dealing with realistic image sizes, there's just no way you can use an ANN approach. We have to use this convolutional neural network approach. Okay, coming up next, we'll focus on training the model. I'll see you there.